All right, let's just dive right into this explainer. We're going to be exploring the hidden, almost mathematical poetry that governs literally every moving thing around us. From the blood pumping through our veins right down to entire galaxies spinning out in the cosmos, motion is the fundamental characteristic of our universe. So today, we're unpacking the science of how things actually move, and we're going to translate those everyday observations into clear, completely understandable physics. Think about this for a second. Have you ever been sitting in a stationary train at a station and suddenly you feel like you're moving backward, but then you look out the window and realize, no, it's actually just the train next to you pulling forward? It's a total mind-bending illusion, right? Well, that happens because motion is entirely relative. We really only know we're moving by comparing ourselves to a reference point, what we call an origin. Like a passenger in a moving bus sees the trees zipping backward, but to the person sitting right next to them, they're perfectly at rest. So, here's our agenda for today. We'll hit distance versus displacement, speed versus velocity, understanding acceleration, graphing our movement, the equations of motion, and finally, uniform circular motion. Okay, moving right into section 1, distance versus displacement. Basically, where exactly are we? Now, here is an absolutely crucial difference. Distance is simply the total path length covered. By an object, if you take a winding, twisting road to the store, your distance is literally every single meter you walked. It completely ignores direction. It only cares about the magnitude. Displacement, on the other hand, well, that's the shortest straight line path measured directly from your initial starting position to your final position. It absolutely cares about direction. It's basically the as the crow flies measurement. So think about the number 0 for a minute. I'm going to challenge your intuition here. Imagine you grab a long rope and walk all the way around the outside edges of a basketball court, and you finally stop exactly at the corner where you started. You've walked a pretty large distance, right? Dozens of meters for sure. But because your final position is the exact same spot as your initial position, your total displacement is just a perfect 0. Crazy, right? Which brings us to section 2, speed versus velocity. Just how fast are we going? Much like distance and displacement, speed and velocity are totally used interchangeably in everyday life. But in physics, they are strictly separated. Speed is simply the distance traveled in a given unit of time, like kilometers per hour. But velocity is basically just speed that brought a compass along for the ride. It's the speed of an object moving in a definite, specified direction. Let's look at a swimmer named Usha. Usha swims from one end of a 90-meter pool to the other, and then back again. So she's covering a total distance of 180 meters in exactly 1 minute, or 60 seconds. Her average speed is that total distance divided by the total time. So 180 divided by 60 gives us an average speed of 3 meters per second. But hey, remember our basketball court example. Because she returned to her exact starting point, her displacement is 0, and therefore her average velocity for the entire round trip is literally 0 meters per second. But let's be real. What happens out in the actual world? Objects rarely move at a perfectly steady pace in a perfectly straight line, do they? You're braking for traffic, you're turning corners, you speed up to pass a truck. So what exactly happens when velocity doesn't stay constant? That leads us into section 3, understanding acceleration, the whole business of speeding up and slowing down. By definition, acceleration is a measure of the change in the velocity of an object per unit of time. If you drop a stone from a building, it falls with uniform acceleration, meaning its velocity increases at a totally constant, steady rate. But if you're driving a car on a super crowded city street, hitting the gas at green lights and slamming the brakes at red lights, you are experiencing non-uniform acceleration. Let's demystify the math behind this real quick. The formula for acceleration is a equals v minus u all divided by t. In this equation, v stands for our final velocity, and u represents our initial starting velocity. So we just subtract the initial from the final to find out exactly how much our velocity actually changed. And then we divide that by t, which is just the time it took for that change to happen. Pretty straightforward. Let's ground this math in reality. Imagine a guy named Rahul sitting on his stationary bicycle. His initial velocity, u, is 0. He starts pedaling, and 30 seconds later, he reaches a final velocity, v, of 6 meters per second. Using our formula, we take 6 minus 0, which is just 6, and divide it by the 30 seconds it took. So Rahul's acceleration is 0.2 meters per second squared. What that actually means is he's actively adding 0.2 meters per second to his speed every single second his foot hits that pedal.
All right, section 4, graphing our movement. Let's start visualizing all this motion. If we track a car's movement over time, a really clear story starts to emerge. At 0 seconds, it's moved 0 meters. After 2 seconds, 1 meter. After 4 seconds, 4 meters. By 8 seconds, it's covered 16 meters. Do you notice how the distance is jumping by larger and larger amounts? This right here is the raw footprint of non-uniform acceleration. The car isn't just moving, it is actively speeding up.
Conversely, if we map out an object moving at a perfectly uniform speed, the graph looks entirely different. By translating the data into a distance-time graph, a uniform speed creates this beautiful, straight, ascending line. This visual elegantly proves that the object's distance is increasing at a directly proportional rate to time. There is no curve, no changing acceleration, just a steady, relentless march forward. Now on to section 5, the equations of motion. This is where we synthesize all our variables.
So when an object travels in a straight line with uniform acceleration, we can actually tie all its variables together using 3 incredibly elegant rules. First, we have the velocity-time relation, which basically tells us how fast something is going to be going after a certain amount of time. Second, the position-time relation, which calculates exactly how far an object will travel. And third, the position-velocity relation, tying distance and speed together without even needing to know the time. These 3 equations are essentially the master keys to predicting uniform straight-line motion.
And finally, section 6, uniform circular motion, the concept of always accelerating.
To really wrap our heads around this, let's do a quick thought exercise. Imagine an athlete running on a rectangular track at a totally steady speed. To stay on that track, they have to sharply change their direction 4 times, right? Now imagine a hexagonal track. That's 6 changes in direction. An octagon? That's 8. If we just keep adding sides infinitely, the track eventually smooths out into a perfect circle. And on a circular track, that athlete is actually changing their direction at every single tiny point along the path.
And this brings us to the grand finale of our physics logic. Remember earlier when we said velocity isn't just speed, it's speed and direction? Well, if you move in a circular path at a perfectly uniform, constant speed, your direction is continuously changing. And because your direction is changing, your velocity is constantly changing. So if your velocity is changing, you are, by definition, in a state of constant acceleration. It's a brilliant paradox. A perfectly steady spin is actually an act of continuous acceleration. Which ultimately brings us back to the ultimate moving object, our very own planet. Just consider the sunrise, the sunset, the changing of the seasons. The Earth spins on its axis and races around the sun in uniform circular motion. We are literally hurtling through space, constantly accelerating. And yet, we feel like we're perfectly at rest. Just like that passenger in the stationary train we talked about at the very beginning. The exact same equations that govern a simple bicycle ride also govern the stars. So the